In this series of video segments, we are going to explore Hooke's law. Specifically, we'll talk about the nature of an ideal spring, what is Hooke's law, free body diagrams in Hooke's law, the Hooke's law graph comparisons, Hooke's law calculations, and the inverse Hooke's law graph. So first, let's explore what is an ideal spring. Well, when we use the word ideal, it means that something is theoretical and doesn't really exist. And this is not only in physics, but in other sciences. However, under perfect conditions, it could exist. But the problem is, those conditions can't happen. So again, it's theoretical, it's impossible. If the conditions were perfect, it could exist, but those conditions never exist. That being said, it's incredibly helpful for things to be considered ideal and to imagine how they would behave. Also, sometimes things are so close to being ideal that we can't detect the difference. So for all intents and purposes, they are ideal. So very often, we assume things are ideal. They may behave very close to being ideal, and so we say they are ideal. So let's consider this screen grab from a PhET simulation and do some defining of attributes. What we have here is a ruler showing length. And you'll notice that there is the length of the spring. And we'll call this the equilibrium length of the spring, meaning without any forces being attached or applied to it, this is the spring at rest. It's its equilibrium length. And the equilibrium length is not important. What is important is when we apply a force and stretch that spring, that it gets longer. So we have our equilibrium length of the spring, we have our elongated length of the spring, which results in an elongation of the spring. Now, the word elongation has some synonyms. The first of those is the displacement, which is denoted delta x. If we set this to our equilibrium point, 0, then anything that is in this direction is positive, and anything in the other direction is negative. So if we apply a force in this direction, it's positive. If we apply a compression force in this direction, it's negative. If we displace it in this direction, it's positive. If we displace the spring in this direction, it's negative. So we can refer to the displacement, the elongation of the spring. If we look at compression, we again have our equilibrium length of the spring, and we can apply a force where we shorten the spring. So we had our equilibrium length of the spring, our compressed length of the spring, and now we have the compression of the spring, or the displacement, delta x.